There you go. So from this website, crackmes.one, this is gonna be a warm-up exercise, so you can get familiar with the tool. Get it from here, and the password. There you go. I shared the link through the chat on Zoom, and the password is gonna be crackmes.one for the zip file. So download it. So download, then you have to open it, extract, and then the password is crackmes.one. And then as I also have here, then you will have this bricked up exe, and then you can let me do it again. So I'm gonna close the debugger, open the debugger, and you want to open X32 debugger, and then drag and drop it here, yeah, and then it will be open there. Or you can open it from here. I'm gonna do both. So the other option will be to go to File, Open, and navigate to your binary, and then Open. All right. I'll give you a few minutes, guys. So do that. Just get it open, and then we're gonna start looking around this binary. And then at the end, we will try to solve this crack me. It's a warm-up exercise, so you can get a little bit warm it up, as I said, within binaries and within reading some assembly right before jumping into the exploits. So I'll give you a few minutes.
Juan, I don't know if you can hear me, but I think yeah, like Ahmed was saying, like but your mic is off, so like we don't hear you.
Oh, oh, snap, guys.
I'm so
So
sorry.
no, it's fine. Sorry for you guys. So I just gave the explanation. I will have to do it back. Thanks for interrupting me. Otherwise, I will continue an hour like that. Let's go back. I think I was where I was. I choose from the beginning, right? All right. So we loaded this here, and then what happened is that well, it loaded the binary, and then the breakpoints are added here, and there are some breakpoints that are added automatically by the preferences of this debugger. Not every debugger does that, but what mostly every other debugger does is that it adds a breakpoint on the entry point of the program. So x64 debugger, it also add these two breakpoints by default, TLS callbacks, and you can remove those by pressing deal or super from your keyboard, and then you will end up only with one here, right? And if I remove that one as well, it will choose don't break and will execute the program itself. So now if I go to CPU and start the program, the only breakpoint that is going to hit is going to be this one, the one on the entry point. So run, and now it's hitting only that breakpoint. And if I continue execution now, it will ask me for the input password. And now it's executing the program itself. Then next to breakpoints tab, we have the memory tab with the sections of the program and the permissions here on the right that we have for this program. And you can see that not all sections from this image or mapped can be read or write, and then you have different permissions. There is quite a difference between the user memory space that is listed here and the system memory space within the permissions and the access that you have. Here's one in the middle, but still. Then right after that, you have the call stacks log for this program. And this is something that we're gonna look later on during the exploit development process. That is the list of structure exception handlers that we have on this binary, and where are they coming from. In this case, we have two memory addresses for two exception handlers, and they are both coming from NTDLL. That is a library from Windows. Script, if we have something scripted for the debugger, and this is just only for this debugger, of course. Then the list of symbols, if we have symbols loaded for this, but of course we don't. But let's say this could be quite useful if you want to write your own, let's say you write your own crackme in Visual Studio, then you can export your crackme with symbols, and then you can load the symbols here, and it will be easier for you to read. Source, again, if you have it, then you can load it here as well. References, same, and the threads that you have running here. And we have only one, that is a main thread, right? Handles, you can have a list of your handles here. Trace, if you are tracing something, and Snowman is a tool for decompiling within x64 debugger. So when you decompile something, it means that here we are actually reading the opcodes here. So these are the opcodes. See, these are the assembly codes, and this is the opcode. So basically, we are in sort of a way decompiling it because we are reading the opcodes. But you can also decompile it in another type of languages. The typical language that is used when you decompile something is C or pseudo C. So it doesn't matter if the program is compiled in a different language. In most of the cases, when you decompile something from opcode, so from assembly, you will get a pseudo C or C code in the best case scenario, where you can actually try to read the language instead of just trying to follow this. Assembly is not that hard to follow, but if you don't understand the basics of calls and how the functions in assembly work, it might be quite hard to follow. But if you use a tool like Snowman, in this case, is gonna try to make it C++. That's what it says, Snowman. Then you can use that. If you don't have a Snowman available for you or a tool like that, uh, IDA Pro, if you have a license, they have X-Rays as a decompiler, or you can use Jydra as well. So let's do that. Actually, we have the time, so let's open this RACME in Jydra, and let's see if we can read it from Jydra as well. So let's add it here. The intention of using Jydra is to make use of the decompiler of Jydra. Jydra also has a debugger, so you can also use it for both. But what we're gonna use now is the tool for static analysis from Jydra. So you want to analyze now? Yes, that we select analyze everything. And if you don't know Jydra, Jydra is a tool from NSA, from America, and then you can get it here. Again, I click on the correct link. There you go. And here you can choose get it. And same with exploit pack, you will need Java JDK. All right. So same with Jydra. So what happened here is that I load the binary into Jydra. Jydra analyzed the binary, and then it took me right into the main function that Jydra has detected, right? So here in Jydra as well, we can see the imports that is using is kernel32dll, msbcrt.dll. We can see the exports, and inside the export, surely we will find the main function as well. So the main is here, and then the other exports for this program. And this is the main. And if we follow along the main, we will end up with what Jydra was showing us at the beginning. Then the functions that Jydra has identified, and in the case that Jydra can identify a function name from a library or from the binary itself, then it will try to assign the name of it. So it's easier to read for the reader or the reverse engineer. Uh, and here it says initialize critical section, delete critical section, and all of these have been detected and correctly analyzed. Here we have a printf, so we can have a look of what is this binary doing. Main, memcopy, so it's using memcopy somewhere here. It's calling memcopy, but then we have functions that doesn't have been recognized. Of course, this is the main function. We know that already, so this is part of the main function, and it's assigned a memory offset, so it's 0040,000. We know already that that is the memory offset for the main, but it added fun and then the memory offset. So if you have more than one function that doesn't have been recognized by IDA, then we'll always do fun. That stands for function, and then the memory address of that function itself within the binary, right? So then labels, classes, namespace, and so on. And here we have the sections, the text section, header, data, so on. And right there, as soon as we click something on the right side of the screen, you can see already the decompiled code of this binary. So this is pseudo C in the case of the compiler of Jira. And of course, you can also follow along and double click to understand here what it does. So you can also go back to other functions, but I double click on the main function. And you can see here that I already found the input password. Here, print is doing main. So this is where we were. And then it's going right after that here into main, and then it's returning, asking for the password, and then choose showing up on the screen, choose like we seen here. So asking for a password, and then it's doing a comparison of some sort, and then dropping off. So uh, that's something that you can use. So if you don't have a decompiler, you can open the tool into Jira and then use it there. Or you can also use Snowman. You don't need to decompile it if you know how to read assembly, of course. But if you want, you can also, if you want, and if you have the pro version of IDA, then you can also load it into IDA and then follow along here. So here's the same scenario. It's a debugger and a static analysis tool. Same with Jira. Jira also has a debugger, but IDA Pro will show you. It will show it in a different way. On the left side of the screen, we have again the function that has been recognized by IDA, and then IDA, instead of adding the name, it has recognized that this is the main function here, and then it's showing me this is the main function and added main to it. And remember, in Jira it was showing the function and the offset, right? And same with Jira, it took us to the main part of the program. And same as with Jira, we can double click the functions and go back to where we want it. So if we go as well to the exports, we can jump into the entry functions. So this is the entry point of the program. And then if we follow along, we will end up in the main function. So double click on the startup and then follow along this. And then at the end, at some point, it's going to call main. See here, and then it's going to start and then following along. But let's also try to do decompilation so you can see the difference. Let's go to the main function. And then here's the main function in IDA, and here's the pseudo code in. It's not clicking me. I have the zoom window over the.
Juan, I think you got the mic thing again.
Oh,
Yeah,
now
now you're
it's.
back.
Oh, perfect. Yeah, what I was saying is that same with Jira does it by default, so it syncs the assembly with the decompiler. But if you use IDA, then you have to sync it yourself. So drag and drop one next to it, and then as soon as I click memset, it will take me to memset, and it will show me what part of the assembly code corresponds to memset. The case string copy here corresponds to it, and you see that it's quite easy to see what it's doing from the decompiler, but from here it's not that easy because we have the representation of this string that I assume is going to be the string that the program is asking for in the hexadecimal representation. But something that you can do, same with Java, is to change the representation. So if I press the letter R, it will change it from hexadecimal to ASCII. So I select it, and then as you can see here, a string copy, you see that it's doing this string into this variable. I double click the variable. So this string into this variable, but when you see this in assembly, it's taking a bit more, I think a bit more effort, right? So it's constructed this string. So basically, it's saying S700, the amount of string moving into this pointer, and then REPU is moving it into this pointer, and then the last part of the string moving it into this pointer, and then doing a load specific address of that into EDX, and then just move it that value so you can get the actually call to string copy. So that's how a string copy works when you call it from assembly. And same with scanf. If I click scanf, it shows me how it's constructing this scanf. Scanf is a function in C that is used to get the input. It's used to get the input, right? So, but how does like that it works in assembly, but in code. But when I read it in assembly, it works like this. So first is constructing this. It's constructing this parameter. So then right after it has all the parameters set in memory and in the registries, then it's at the end of it is gonna call the scanf function. That actually scanf is not a call directly, but is linked. So if I click scanf, it will take me into where it's jumping into. And because I click on it and the program is not running, it cannot find the reference. So when I run it, the program is going to load those libraries into the program, into the memory space of the program, and then I will be able to do the jump and go into the library itself. Can show you working this when we look at the string comp, right? Because here at a glance, you know that this is the password, and because you can understand this, right? So it's basically printing this into the screen, then asking for a password. It's gonna move into string 2, and it's gonna be a string type, and then it's gonna copy this is to string 1. So you have string 1 and string 2 that are declared here, string 1 and string 2. With a buffer size of 100, and then it's gonna do a mem set of that, and it's gonna basically do a string comparison between the string 1 that if you double click you can find out where it's gonna be placed on memory, but a string 1 and string 2. And then if this result ends up to be being true, it's gonna do not okay or okay. Yeah, and that's about it. That's what it does. Here's a trick. If you want to follow along here, use the colors in your debugger. And then for this, for example, this is gonna be the one that we wanted to reach. Is the one that says okay, and the other one is that said not okay. So here we put it in red. So that's not red. So that's the one that where we wanted to go. All right. And same, you press F2 as with here. So you press F2 or set breakpoint to set a breakpoint, and something a way to start if you don't know where do you want to start, you can dump strings. And then here you can see all the strings that are C recognized. That's why you have the type C. So it has to be a C type string, meaning that it has to be a string that can be interpreted by the C language. And then you can choose follow along these strings. And use, if you find a string that might be interesting, for example, input password, and you don't know where this is, let's say you didn't found this as easy as us, then you can double click on the input string, and then you will find in the data section the string and follow the references for that string. So I click X here, and then I will see the cross ref. That's why it's X ref, because it's cross references. I could have more than one because the string can be used in more than one place, but in this case, it's only used there, and it is already taking us there. Right. So here's a trick. If you are doing a CTF in and there is a program that is constructing a string, or is doing a keygen or something like that, but at the end of it is using a string compare. Instead of trying to understand, here is quite easy because it's just using string copy to create this string and then dumping the value into string one. But instead of doing that, if you see a string compare inside a crackme, then you can choose go inside the string compare, because the string compare function is going to actually receive those two strings. Then, for instance, some crackmes where they try to become harder for the reverse engineer to solve it. Then some tricks that they do is try to make the string more harder to read, or is constructed the string from temporal places, of constructing the string from a non hard-coded place. In this case, it's just hard-coding the values into memory, but let's say it's creating the string based on the input of the user or something like that. But if at the end it's using string compare, you can just jump into string compare. That's what we are gonna do now here. So we're gonna press F9, execute it, and then as soon as we type a password, it's gonna stop the execution in the breakpoint that I set. So if I show the breakpoints here, I have a breakpoint set here on string compare. So now I'm gonna type a password, and now the execution has been stopped into string compare. I'm gonna go inside the string comp function, pressing F7. And then this is what I was showing you before when I was showing you the libraries and the champs. Because remember when I click, just like a few minutes ago, I click on a function and try to jump into that function. But because that function is externally linked, I can only jump into that function when the program is actually running, because the libraries for these programs, they are externally linked, right? So now I can do that. So if I press F8, this jump is gonna go along, and it's gonna jump into this library that it was externally linked. So msbcrt.dll, and now I'm inside string comp function. So string comp function will get two input parameters. So edx is one, ecx is the second one. So as soon as start the function to do the actual comparison, you will see that already here inside edx, I can see the value of the string, right? That is this first comparison. So something that you can do if you are doing a CTF, something useful is to create a IDA script, or a script for it could be also a script for x64 debugger. And then if you are doing a crackme, this is just a tip outside this training, just create a script that will check if the program is using a string compare, and if it's using a string compare, dump the values of edx as soon as it enter string compare. So then you will have the password just right away. if it's using a string compare. So if we continue the execution, but we will go back into here. We're gonna press add a breakpoint here to see if it worked. So I'm gonna stop it. Now that we have the password, we're gonna type the password, and if this works, then it will go into the green. And as we guessed, now is calling puts, that is basically printing something on the screen again, and I assume that it's gonna be the okay. Yes, there you go, and that's it. That's it for IDA, and same here. So you can I already loaded here. So let's do right click and search for current module uh, string references, or you can do it for all, but that's for NTDLL. Let's restart it. Now it's the breakpoint 1 on the callback 2, and then on the main function. We can do it for the current region. So what I did is right click, search for current region. So instead for everything, so it's a little bit less to read, and then string references. Basically, I'm dumping strings. So right click, current region, string references, input password, and then if I double click, it's gonna take me there. There you go, and it's taking me directly to the reference of a input password. And here, let me check, because here we can also have it on a graphical way somehow. View graph somewhere here. It needs to be running. Well, in any case, you can have it as a graph. So basically, a graph is with the boxes, so it's easier to read the flow, because otherwise the flow, you will have the flow here on the left side of the screen. You can see here, for example, let's try to find the okay. It's, the jump for the okay. Now we are on the entry point. We're gonna go again, current module, string references, and then we're gonna go here. And here we can see the jumps that we were seeing before. Okay, here's the jump for the puts, and then the other jump for the program. So it starts here. Input password. It's calling printf to print the password. Then doing the scanf. Then right after that is loading the values of the string. And then something that we can do is exactly the same, is going into inside string compare. So we can continue execution, type something, and then if we go inside string compare, and we go into, now is the jump. Well, the thing is that Oli DBG, sorry, Win64 debugger, it also shows us here on the right side of the screen the values of the memory, and also here. So here we can see that this is our input, and this is the values. So if we go there on EDX, now it has populated the value. So inside EDX, we have the 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 input that is expecting. All right, guys, gonna give you a few minutes so you can choose what I did here in your favorite debugger, or you can use X32 debugger, choose like I did. If you have any question on how to do it, and how to solve it. So what I expect you is that you can find the password. So it's not just typing the password there. You have to find the password here in memory, and then of course put it into the crack me and get your crack me done. Yeah. So I'm gonna give you a few minutes so you can do that. And let me open the chat because I haven't checked. Hopefully, yeah. Okay, perfect. Okay, I'm gonna leave my headphones on and the chat open. So if you have any questions, I'm here to help. Guys, just checking if you have any question. Um, Please shoot.
It's fairly okay on my side. Thanks, Juan. Actually, I was thinking when you were doing the program, one alternative way to do it, I mean, I guess it will be more in a CTF context, but when you're using the string compare function down the road in like the assembly instruction, the condition is actually getting evaluated with the GNC jump if non-zero instruction. So another way of like solving it, I would say, is actually patching the instruction to make it right no matter what you're putting in the input. But if we follow your like, regular solving thing, yeah, it definitely like work also that way.
Yeah, that's a way. That's correct. Oh, Austin, I just saw your question. In X34 debugger, what buttons allows continuous execution? Oh, sorry. Yeah, I think it's better if you get the microphone so you can get my attention quickly. So let me. Oh, there you go. So basically, in any debugger, I get your questions. I will choose go to it. So in any debugger, you can stop the execution, restart the execution, continue the execution, and here if we go to debug for the case of x64 debugger, you can run basically continue execution or press F9 in your keyboard, and here you have the shortcuts for your keyboard. So these are the interesting ones that you need to use. So it's basically run is the first one. Run untick selection. Oh, sorry, I'm also drinking coffee here. So pause the execution F12 and the same. They are not standards, but every other debuggers use the same keyboard shortcuts. So step into if you want to go inside that function. For instance, if you want to go inside the string compare, then you after you reach the string compare breakpoint, you have to press F7 to go into, then F8 to step over if you want to choose jump over that one, and then execute the return. That will be the one that you ask for. So Control F9 in the case of x64 debugger. I hope I answered your question. I think it's a few minutes too late. Maybe you already found the answer. Guys, anyone else has a question? Has have everyone already typed the password correctly? Because otherwise we have to jump into the exploits because we are running out of time. uh, uh, so let me see those answers on the chat or on the microphone. Everyone got it? I see Fenai got it. Awesome. Awesome, Austin. Great. And what about the rest? Nice, Enzo. Well, good job. Awesome. All right. Um, then if you guys don't have any more questions over the crack me, we're gonna jump into the exploit part. So this was a warm up, a bit extensive, but I think it's quite useful, so we can get our hands dirty with the debugger because that's our day to day when we are doing exploit development. All right. So let's do first the exploit for R, and then we're gonna jump into the other one, into Echat. All right. You can see my mouse, right? So if I move this window, awesome, perfect. So let's do that. So we're gonna open the 32 debugger with R. So with any other debugger, you can do exactly the same as I do. So you can go into File. I have it already on recent files here, RGUI, the 32 version, or you can attach to it, right? If you have the permissions too, so of course you need to have at least the same permissions as the program that is running. In the case I do, because I'm running as a user here. So I can do File, Attach, and then I'm gonna select this program, RGUI, and then click on Attach. So now the program is still running, of course, but I can stop the execution at breakpoints or else. That I can do is stop it, and then I will do it in the other way. So loading into the debugger itself. So any way is a way. I will work as well. All right. So if I go to, I remember to the exploit that we got from exploitdb. So this one, it wasn't working. So we need to rewrite. Need to rewrite the exploit. So what we're gonna do, I already have it here, so we can skip the writing. Here I have a crash. So this POC, it will only reproduce the crash so we can see the buffer overflow happening and we can trigger the vulnerability. So I close it too quickly, so I don't think you were able to see it, but here it is. And don't worry, guys. After this training, I will also share the scripts. So here we have fopen. I'm gonna choose do crash.txt and then create this file crash.txt. I'm gonna create a buffer. It's gonna choose a variable and then I'm gonna write into that variable a capital letter A. So it's 41 is the hexadecimal value of A, and I'm gonna do 3000 because at this point I just want to trigger the buffer overflow. So then gonna write into it. So I was using f as a variable and then gonna write into it. And this is gonna write into this file with write access as binary. So WB and then just close it. So if I do that, if I run it, and then I should have a crash file here somewhere. There you go, with 3000 A's. So copy those A's. I'm gonna run this file. And if you are too lazy to write the Python script, you can just dump a bunch of A's into your notepad as well. So I press F9 to continue the execution after the first breakpoint. So remember, if I go to breakpoint, I can see the breakpoints that I have, 9, 9, 9, 9, and that the one that I want to reach is the entry point breakpoint, and then continue execution. I will get the program, and then until the program is running, there you go. Or I can choose go ahead and delete all the breakpoints so I don't have to press F9. So that's up to you. Then I go to edit GUI preferences and I'm gonna do a control B or paste my A's here. So I already have my A's there, 3000 A's. I will press OK, and then the program has already overflowed. So if I see here on the CPU side of it, I see that I already overflowed some registers. In the case of EBX, is overflowed by 41, 41, 41, 41. Here I can see on the right side on my screen the stack representation. So it's full with A's, so 3000 A's. And if I look into the execution handler, the structure exception handler, I see that also I have also overwritten the exception handler with A's as well. So I have here the next memory address for the execution handler that is also A's. And here the pointer to the stack pointer for the stack, it's also showing me the A's but in ASCII. And here's the stack, as I said, and so on. So and most important, if I look at the instruction pointer, that is exactly what I meant to. The instruction pointer it has in an E at the beginning because this is not 16 bits, it's 32 bit. That's why it has an E in the beginning. So it's extended instruction pointer. That's why EIP, but instruction pointer is but extended. So that's why what I have here 41, 41, 41, and the instruction pointer it has been taken from the stack. So it has been taken from here, and then it's jumping. It's gonna try to jump there. So and actually it jumped into there after the execution happened, and then it's showing to me that it's trying to execute this instruction 41, 41, 41, and of course that instruction .exec is nothing, is throwing an exception access violation. If I press F9, what's happening now is that you see that this changed. Now it says first chance exception on 41, 41, 41 because the structure exception handler where I am now is also pointing into 41, 41, 41, 41. So what is a structure exception handler is a try catch, basically. And if the cache is also overflowed, the program doesn't know where to go. So that's what is a exception handler. So it tries to catch the exception, but because the values for the exception handler are also stored in the stack, then I can also override the values of those exception handlers. So first, I do a buffer overflow. Second, I overflow the stack with my buffer overflow. Third, I overflowed also the values of the exception handler because those values are also stored in the stack. And then the exception handler is taking the lead and trying to take control of that exception. That is the first buffer overflow. Then it's trying to take control using the structure exception handler, but it fails as well because the exception handler also has been overflowed, and now that's we see here the first exception, and then the first chance is trying to go, and then the second is also failing. So first exchange, and then it's trying to go, but it's failing, 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 and continually failing. Let's go back on that again. So it will be clear. So we do it for a second time, and I want you guys to do it as well. So I'm gonna do it as well without the Python. So you can also reproduce it yourself. So remember, you load here the argui here. I will press F9, 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 or alternatively, you can choose remove all your breakpoints and then choose continue the execution, pressing F9, and then you will have the program running in the background like that, and then going into edit GUI preferences, but because you don't have the Python file, let's choose create some A's. So it will be the same result. So here on the column, you can see the amount of A's that I have, and I'm gonna do, okay, 9,000 or something similar. So I copy my 9,000 A's, I'm gonna paste it here, press OK, and now if I go to my debugger and I try to continue the execution, it says first chan exception here, right? And I have if I can double check it by doing the check on the tab of the structure exception handler. Please do that, guys, and let me know if you have any question on this. And if you don't understand the concept of the structure exception handler, ask me now so we can follow to the next step that is going to be changing the buffer overflow into an exploit. Just do it this now. All right, guys. Have you managed? Sorry if I don't give you enough time, but we have a lot of ground to cover. All right, so let's continue with the exploit. Close this. All right. Um, so we were here, right? So this is the crash. So we have choose created the crash and reproduced the crash, overflowed the stack, and also overridden the structure exception handler because of the stack, right? And next, what we're gonna do, the next step will be to get the values and the offsets of where are we gonna be able to override. So because as I mentioned, we were able to override EBX, EIP, the exception handler, and maybe something else. So in order to do that, we're gonna use, in order to understand that and check for the offsets, we're gonna, instead of using A's, we're gonna use a cyclic pattern. What is a cyclic pattern? It's a non-repetitive pattern of basically a string, a long string. But if you see this, it's non-repetitive because every seed is non is different, right? So every other string is different to the one before. So why do we want to do that? Because then after sending this into the buffer, then we can check for, hey, where is this on memory? And let's say this is the value that we get from for EBX. Remember, we were overflowing EBX and also EIP, and say, okay, this is the value of EBX that we see on memory. So if we count the characters from here that we see on EBX until the beginning, and we get the length from here to here, and you say it's 1000, I don't know, 2000, then we know that after using 2000 something or junk, then we can have control of the values of EBX or EIP, or most important for us, the structure exception handler. So we're gonna do that. So we're gonna create this file, or we can choose copy this string, and this string can be created using ERC. That's why we are using ERC. So I created this string, and it was going into crash.txt, and let me give you the commands. So this is the command for creating the pattern on ERC. So if I open here x64 debugger again, I'm gonna load the program, and then here you have commands. You have to first set the config directory. In this case, for you, it's gonna be something else. It's gonna be your user, and then folder or desktop. You can change that for to be more adequate for your environment. And then you type that on the command here. And then if you go into log, you will see the output. Yeah, it says that it's now registered, and I have ERCXDBG working. If you don't see that, it's because you didn't copy the plugin from ERC into the proper folder. So remember, it has to go into here, into the plugins folder. There you need to have ERC. So the DLLs for ERC, these ones, yeah, the libraries. Well, I do have it, so I can either create a pattern here, but I already have done that, so that's why I have it here on here, or I could just paste it, but I already have it here because I put it inside inside a Python script. So let's run it and let's use the pattern, the cyclic pattern. And then we're gonna do edit GUI preferences, and I'm gonna paste the pattern. And as you can see here, if I press OK, now I reach the exception, but exception of course is instead of pointing 41, 41, 41, 41, I haven't sent A's, I have sent my cyclic pattern that you can actually see here, and my cyclic pattern is on the stack. Now what I'm gonna do is the next command, that is find NRP. So here logs, there you go. And now it's going to take some time, but after that, it's going to tell me exactly where it has been, my cyclic pattern has been found, basically the offsets. So now here I know, here, this is the output. So it says that the process name, error GUI, find RP table generated here, and also I should have a log of that here somewhere. Yeah, here, find RP. And then it says that the SE points into the parent position 0 for 2999. But what is important for us is to know that the instruction pointer, these other registries, we do have access as well. They are mostly common registry, so and global registries. And also the SEH registry is overridden with pattern and position 1012 in the same thread. So see, this is the main thread, and it's the same thread that we are using. So it's basically the RGUI application thread. And then this is what is important for us is the 2092 of the instruction pointer and the 1012 of the structure exception handler, right? By using that, then we can construct a basic here, a basic exploit structure. So remember, we came first with this one. This is the POC. So we started with this one. This is the POC, and then we came to the pattern. That's the second one. So we replaced this for the pattern. The ACE has been replaced for the pattern. Then after that, we run find NRP to find the memory offsets, and then by knowing the memory offsets, we can start crafting our basic structure of an exploit, SEH type of exploit. All right, so 1012 is the value for EIP here. EIP is overridden with pattern and positions. Here exception handler, SEH. Because remember, as I say, we are not going to do a buffer overflow, even though we could, right? We could do a buffer overflow here, but the structure exception handler is going to try to take over, right? That's why here we use 1012. So we are going directly into that, right? So after we overwrite our instruction pointer, that is basically the structure exception handler, that if you have any questions over that, please ask now. Then right after that, we are sending the two new values for the exception handlers. So it's going to be AB, AB, those in hexadecimal is going to be 41, 42, 41, 42. And then the second exception handler is going to be DD, DD. Yeah, that's 44, 44, 44, 44, 44, 44 in hexadecimal. And then we leave some space for the shellcode. Because we started with 3000, remember our POC started with 3000, so it could be any value. So we are taking 1012 less for that chunk, minus 8 because these are 4 bytes and 4 bytes. So we are just uh, taking out that from our initial buffer of 3000, right? So we don't know exactly why we use 3000, but it could be 2000, 4000, it doesn't matter. It's a hard-coded value that we use it to trigger the buffer overflow, right? So if you don't know the value, then you can just start 1000, doesn't nothing happen. 2000, nothing happened. 3000, hey, something happened on 3000, then you stop there. You can continue to 4000, 5000, 9000. That doesn't matter. So here I could use less, but if you overwrite way too much, then it's not gonna be as easier for you, and you will have a more heavy exploit in terms of memory size. So you want to use as less as possible, always, right? Okay, so we are sending 3000 as a hard-coded value, and then just taking out these 4 bytes and then these 4 bytes from the structure exception handler and the chunk that we are using in order to reach the structure exception handler, right? So at position 1012. So now if I run this, what's going to happen is I'm gonna reach the exception handler, override it, and then these two values should be here. They should be here. So if everything is correct, that's what should happen. So let's try it. So I'm gonna run it. We say it's the basic one, crash. And as you can see, those are the 1000 something A's, then 3000 minus something, and then those are my AB, DD. I'm gonna copy this, restart the execution of the program, continue, and then continue the program, edit, GUI, and if everything goes as planned, our exception handler should be reached with 41, 41, 41, and then the values for the exception handlers inside the exception handler tab should be different, should be AB, and DDDD. So here is correct, 41, 41, 41, first chan exception. So remember that this is not the buffer overflow. This is the value for the first chan exception. If you want to see the buffer overflow, then then you need to use the value for the EIP, that is 2092. That's why, but you see A's in any case on EIP because we are in any case overriding the values of the instruction pointer, right? But if we type 2092A plus DCBA, then we will see 44, 43, 42, 41 here, but we are not using it. So we are completely avoiding that because this is not a buffer overflow exploit, it's a structure exception handler type of exploit. So we are still overriding this, but we are skipping that and it's going directly into the first chan exception, into the exception itself. That's why we see the 41, 41, 41 here. And let's check the structure exception handler. And there you go. We have our 444444 and 42, 41, 42, 41. That is equal to what we sent here. There you go. 44444, this one, and then 4142, 4142 there. But so far we are just sending trash, right, to the program. So now we want to start doing something. So that's gonna be our next. Is this one? Okay, this is the next one, is without the shellcode, right? So here we have again, we are just sending 2092 for the instruction pointer, but we don't need that. So just like I mentioned, it's just 2092. And here, this is just to show you guys, but we don't need to add this because this is just pure junk. that we are sending, because what we want to reach is the structure exception handler. Remember, this I'm gonna be adding here, but I don't need to. This is just to show you here that we're gonna reach the overflow, and then we can control also the instruction pointer. But not only the instruction pointer. Remember, we can control a bunch more of other registers. For example, EBX. We could also at position 288. So if I add 288 and then something else, I could choose show you how I control to EBX as well, right? That's a back pointer. So let's run this. So basically, what you're gonna see here is that the EIP is gonna be overridden. So here, the instruction point is gonna be overridden with the DCBA, and then I'm sending again 712 A's. So if you sum this up, is gonna give you 1012. That is the value that we need to send as chunk to reach our exception handler, because it's an exception handler exploit. Next, instead of sending AB, we are going to actually send something. Remember that the first exception handler that we're gonna get is gonna be this one. So this one is gonna be a short jump, because the exception handler, this is gonna be run automatically, yeah, after the exception handler takes over, just like with a buffer overflow type of exploit. This is going to be executed directly. So what we want to execute, because we need, in order to don't crash the program and follow the flow, we need to run the two exception handlers. So the first exception handler, we're going to do a jump, yeah, that EB null B stands for short jump. So your jump, short jump, is EB OB in as an opcode, and then choose filler so we can get the 4 bytes done here. So 9090 as a filler, but this is what we are going to execute. That is a short jump. This short jump is going to do a small jump, as it says, a short jump into the next execution handler. And this next execution handler, we change it from AB to pop red, and it's gonna pop red the values, so we get execution from the stack, right. So, and after that is gonna try to execute this, but of course it's gonna fail because there is nothing else to execute for BBB. And here we are still doing the same math. That is 3000, that is our hard-coded value, minus the offset for the structure exception handler, that is equals to 716 plus 292 plus the 4 bytes of the value of EIP. Then if we want, we can remove this and say only 2000. We can also do that. So, but for the sake of the training, I want to also show you how we are also taking control of the instruction pointer. And -8 because that's the amount of bytes that we are using for the first exception handler and the second exception handler, and that's gonna be the multiplier for B's. Yeah, let's do that. So this is gonna also create crash.txt. So let's run it, and then we have crash.txt with this, and so we're gonna run it again. And then I'm going to show you how to get those pop red values. So there you go. And if we go here, and now we are here on the first section, but we are not on the, we are already on the exception handler, guys. We are not on the buffer overflow. We are already on the exception handler, even though we overridden the instruction pointer with what we wanted. We are already on the exception handler. If we check on this, these are our values with the short jump and then the value for our pop-up red. That right after this, I'm going to show you how to get those pop-up red values out of the binary using ERC, of course. So if I continue the execution, I get the first exception, and then there you go. And then the program, of course, crashes because there is nowhere else to go. So how to get the values here under commands? If I'm on the program, I can use ERC minus minus ch going into log. And if you don't remember something from ERC, you can also do ERC minus minus help, and it's gonna give you, and it's gonna throw you the menu with the help. But if you want to see the values that you can use for SEH type of exploits or pop-up red instructions, you can use this. And also, it's quite useful ERC, as you can see at a glance. You can also construct a rob chain, so you can, or you can use rob gadget. There are other tools to do that, but ERC has it all. That's why I'm showing you ERC as well. So now it's gonna take a while, but then it's gonna dump a file with the values that we can use for pop-up red. And remember, we want to be universal with these values. So you have to pick pop-up red values that are part of the program. So if already using those values, already running something from the program itself, it stands for return-oriented programming. So this is gonna be like a small gadget that you are running. So it is a small gadget because you are running something from the memory itself. So you can say by doing this type of exploit that you are already doing your first rob chain. Well, you are not chaining it. Well, actually, you are not chaining anything, because the first one it is hard coded, and the second one, this is not part of the program, so you are not returning to anything. But this one, you are doing that. So why did I pick this one and not this pop-up red? Right? This is a pop SE, pop EBX red. Why I'm not picking this one is because this one is from C Windows System 32 that is loaded into the same memory space of this program, but is coming from Windows Storage.dll. And you don't want that because you want to make it universal. So you have to look for either a library that comes with the program itself, or directly from the binary. In this case, is coming from the binary, so argui.exe, and that's why I'm picking this one. But it will be safe to use one of this one as well, for instance, right? Because it's coming with the binary itself, with the bundle of the program. Icon b.dll, it will be safe to use, but don't use this one, for example, from Windows, because then if you share the exploit with someone else and has a different version of that DLL, then it's not going to work because the offset is going to be different, right? So that's why if you want to make it universal, you have to pick something from the program. All right. Next, the filler has nothing. So after our proper red, we want to get execution, right? So we're gonna close it. Oh, I closed the debug itself. Sorry for that. There you go. So what we're gonna do next is to try to get execution. So shellcode is the next iteration. So in this case, so we have still the junk, we have still the 4 bytes that, as I say just a few seconds ago, this is not needed. We can just say 1012, but for the sake of showing you the exploit. I'm adding it so you can see the difference between an structure exception handler exploit and a typical vanilla type of overflow. But then I'm using the these 4 bytes, and actually I changed I changed my mind for some reason, and I'm using this popper red from RELLAPack.dll, but still useful because it's coming from this R program on this version on the bundle. And then right after that, I'm doing the math for the calculating the knobslet, and then creating that knobslet. And right after that, I'm adding my shellcode. And here I added as a help for the user, for the exploit developer. Here, if you add to the buffer right after your knobslet uh, 4 bytes of CC, that will automatically add by the exploit, will be added by the exploit because CC is an interruption. It means int 3. It's the opcode for int 3. That is a breakpoint, a software breakpoint, and then it will stop there. It will break there the execution. And after running all these cycles of CPU, it will reach, so basically the no operations, it will reach the shellcode and then run this shellcode. This shellcode, it will choose do calc.exe. So let's try to see that in action. So we created the crash, and then we need to run the program. And also let's trace it a little bit. So it's not only, all right. So if we look at 41, 42, 43, 44, these are the values for the instruction pointer. These are what is showing because we triggered the exception handler. Here we have the values in reverse, of course, because it's the literal Indianness of the short jump. Then we have the value of the handler itself, right? So this is what executing, and this is the value of it. So if you see it here, this is the value of it. Yeah. And then what we're gonna do, we're gonna say next. That's our exception. And now if everything is correct, we should pop up the calculator. No, I already went. Let me run it again. There you go. Let me see if I maybe I didn't run the correct one. There you go. Crash. That doesn't look correct to me. Oh, there you go. Shall go. Now should be correct. Different file. Now here, okay. And then we have the calculator. But let's try to do it one more time. But I press F9 by mistake. I want to show you. Yes. So when I was looking at On the other file, I was missing the shellcode, right? So I have the A's, and then I was missing the shellcode because I was opening the incorrect file. So this is the representation in ASCII of the values of this shellcode. So paste it there like that, and then if I press F8, I'm gonna continue execution until I get it there. But I can also step into and I can look for the callbacks. Let me do that one more time. Okay, and then we're gonna go here. I'm gonna add a breakpoint here and another breakpoint here. There you go. And then pressing F9, we jump into the pop red. Yeah, so now we are doing pop red, and then when we do red, it's gonna return to the stack. This is now executing the short jump. So now we did this. Oh, sorry. We just did this pop red to get into the stack. And then from the stack, we are jumping over this. Yeah, because this is our value. See, this is on the stack. That's why we are doing the jump, because otherwise it will just crash there. So when we do this short jump, we're gonna jump further our memory address that was also on the stack. We only have the stack, right, to play with. So, and all these values are on the stack themselves, including the values of the structure exception handler. That's why we are first doing this to do the pop-up red, getting back into the stack, and then we are doing the short jump over those values. And now if I continue the execution, it's jumping over over this and a bit more, because that's how far the short jump goes. Otherwise, it should be, instead of a short jump, it has to be a specific jump to a memory location, but we don't have the space for that within those 4 bytes. So after that, then we are reaching our knobs here. And then if we continue the execution of the knobs, we're gonna get the shell code. So I will press F8, continue execution. See, every time I press F8, I get a knob executed. So we have a bunch of them. So I'm gonna scroll a bit, otherwise it's gonna take a while. If we go one by one, go, 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 more, 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 more. And then that is our shell code. So you see, here's the value of our shell code, and starting here, and those are the values that we have. Yeah, BB C716E0 is this, BB C716E0. All right, so I'm gonna put arbitrarily a breakpoint here, just because, so I can continue the execution pressing F9, and I'm gonna reach this breakpoint. F9 there, and I continue the execution so you can see the shell code being executed. Now it's running, constructing my shellcode. And then at some point you miss it, but I'm sure you missed it, but it was passing the argument for calc. And now I get the calculator spawn. I got code execution. All right. So that's it for this exploit. Guys, do you have questions over this exploit? after this training, I'm gonna of course share all these files with you. Any questions over structure, exception handler, exploits, or anything that I did, or maybe a questions over ERC or otherwise? If there are no questions, I'm gonna move into the Echat server exploit. All right, guys, let's get back to hacking. So, how you are handling so far? Because I know that for some of you, it's quite early in the morning. So I assume that you are uh, destroying those coffees.
Yeah, definitely. Quite fine for now, but yeah, I noticed actually we're almost halfway through, but it didn't feel like it, so no, it's good for now. All good.
Okay, that's awesome to hear. But as I mentioned, for sure, I'm gonna share this with you so you can take a step back and then read through to the files and do it at your own pace on your lab as well. Okay, but what's next? Next is gonna be to implement what we learned from the structure exception handler exploit. I'm gonna implement it into not only a remote type of exploit, but also into exploit pack itself. So first we have this application, this easy chat server. There are several exploits for this application. Um, I made one myself like a few years ago, like a few long years ago. You can find my exploit on exploit DB as well. So back in the day when exploit pack was version 10, so it's quite long. We are on version 18 now, but it's also a structure handler exploit. That's why I'm taking it for this exploit for the training. And what is the trigger point for this exploit is the chat PHP function, and then using the username as a value, we are triggering this with a buffer overflow, of course, and then sending our long A's into it, and then completing, of course, this into into the call to each chat server. And as you follow this exploit, you will see that this exploit also has the same structure as the other one. Of course, the main difference is this, right? We are sending this over a socket because it is a remote exploit. So again, I'm using Python. I'm using struct as well. So that's up to you to use struct or not. You can, as I mentioned before, you can choose reverse this and don't use struct at all, but it's easier to use struct. There are other libraries that you can use. One that I really like is Pound Tools to create exploits. So Pound Tools is a Python library. It's used for CTFing, but it's also quite handy to construct and develop exploits. Of course, as a framework, I will use exploit pack without Pound Tools itself, because now I'm gonna show you how the shellcode generator works. And here, if I go to exploit pack, I'm gonna look for that particular exploit. Then I have it here. And of course, when you are running the exploit from exploit pack, you have to follow the structure that exploit pack uses. This is the basic structure, and it's not as hard as with other frameworks. The structure for exploit pack is quite easy to learn. It will only have these values that it needed. So why do we do it this way? Is because we want to be able to run the exploit from exploit pack with or without exploit pack, right? So if you are in an environment where you don't have a GUI, or you don't have JDK or Java, or you don't even want to run the exploit from exploit pack, you can just run it with parameters and arguments and using the libraries that you have. So you can use libraries from exploit pack, or in this case, I'm just using the libraries. Actually, that lib is not needed. You can choose use the libraries from Python in this case, because we are just using struct, string, sys, and socket. That's about it. Um, Here, if you want to replace the shellcode, you can choose call shellcode and then call it from there, or you can use the shellcode generator that I'm gonna use in a few minutes to replace those shellcodes. So the basic arguments gonna be RECL, so it stands for remote, execute code, client side, and local. And then here for this exploit, the XML file only calls for two, so remote shell or execute code, and you can replace all of that here on your edit window of exploit pack and close it. And then all of that is going to be part of the XML file. And it's going to populate those values on the target properties here, right? So the shellcode port is going to be used if you use a bind type of shell. And then, of course, you will need the target and port because this is a remote type of exploit, and it's just taking the arguments here. So as you see, it's so easy to follow, so easy to understand. You don't need to learn a new library or a new way of coding or a new way of making a structure. If you can do arguments, if you can do nested if, or these are choose for if, and then you can choose copy this structure, then you can choose focus on your exploit. And when you want to use your exploit or exploit pack, you add this, and choose the structure to be able to call it. Then you are golden. Then you can choose run it inside exploit pack. Same goes if we are using an utility or something of the like, or for example the TCP fuzzer or so on. So going back to it, uh, um, the exploit itself, you have the chunk that basically we are using the chunk to override the exception handler. Then after that, we have this. So it's 2017 of chunk of A's in this case. 41 is the capital letter A. Then we have again the short jump to jump over this. Yeah, that is again a pop-up red. In this case, instead of using pop-up red from SSL EH32.dll, that is a library loaded by the binary by Echat server. I'm using the same is the same type of pop-up red, but it is a pop-up red. So and this has been found as again with ERC and using struct to pass it correctly. Then the buffer size of it, 2,775. Then a bunch of knobs. Again, I add in this as a debug if you wanted to stop the execution right there. Then the shellcode, well, I have as an argument the shellcode size that I has been obtained through the shellcode generator, and then the two shellcodes. These two shellcodes, one is for execute code and the other one is for remote shell, are gonna be taken as an argument. If you select execute code, then it's gonna pass this E as an argument. So exploit pack is gonna pass E as an argument, and you're gonna get this one. So that's how simple it is. And then right after that, we have to create of buffer, and the buffer is just basically chunk plus the short jump that we have here, the structure exception handler that is the pop-up red plus the knobs there. Then we are multiplying all of this by the buffer size, that is 200, 775, minus the length of the selected shellcode. So by doing this, we can change shellcodes on the fly. Yeah, if we don't do that, then we cannot change the shellcode, of course, plus the shellcode. Yeah, so we are multiplying the knobs. The values of knobs are gonna change depending of the length of the shell of the selected shellcode plus the shellcode, right? Then right after that, remember this is the change. Because this is a remote type of exploit, we are constructing the request that we're gonna send through a socket. In this case, I'm sending this request using socket, but you can use HTTP lib or something of the like. So you don't have to use socket, but of course, to make it more simpler, I use socket instead of HTTP lib or something of the like. So I choose constructing this request. So it's a get type of request, and then this is the first part of it. Then and replacing the username value for my buffer. Then the rest of the request, the password is equals to, and the room and the null value. So that's what is needed to be sent. Then constructing the HTTP request. So basically user agent, this can be changed, of course. The host, I'm taking the target. That's going to be taken from here as from the argument. Is that's going to be the first argument, where it's going to be sent to the port there. Then accept language, accept coding, el referrer. I'm using again the host. Connection keep alive, and then constructing the socket. Here I'm creating this variable that I'm calling socket, the type of socket, and the type of stream for that socket, connecting to host and port here. So host and port. And then right after that, sending through this socket the request that I created here. Then closing the socket. Everything here is part of the exploit function, yeah, and then choose calling it, and there is an exception handler, a general one. If there is an error, it's going to print the error if there is an error. An error could be cannot connect to it, right? Cannot connect to this port or something like that. How to use search is just not required, but if you use less than 2 arguments, then it will ask for those, printing the name of the exploit and the author, and then the hard-coded values for this that host and port, but you can replace it for target and port, of course, because that's what's coming from arguments. All right, let's try to use it but first maybe we can just try to do it manually so you can see it. So let's add this program into, there you go, into the debugger. So now the program is running. So let's try to go here. I have to make sure that it's actually running. And now if I go, and as you can see, you have two options. One is the port through the port 80, and the other option is to SSL port. But I'm gonna choose pick the 80 port. But you can stop the SSL port or stop the HTTP port. So if I go there, now I see it is actually running. So that's the server, and then I'm gonna do this. And then like that. And let's make it crash. And let's open a notepad, a bunch of A's. And here on the bottom part, you can see how many A's are we adding. 1,000, 2,000, around 3,000. Let's go more. And let's see if we can send this through the browser. And I think we were able to, because if we go into the program, into the debugger, now the program has reached the first exception. If we go into SEH, yes, we have successfully also overridden the exception handler here, the first one and the second one. Into the CPU, we can see here that if we press F9, it will try to go there, and we are overflowing the EIX, part of 80, and that's it. This one is not. Oh, and at the end of it, it also got the instruction pointer as well. Right. So now we are at the same stage as before. So what now? Now, now I can test you guys. What should I do next? If we are remember this is the same structure as the other exploit. So what should be the next steps? What should I do? Because now I have the overflow, and what I need to do next? Anyone can give you multiple choice. So one would be get EIP. Two,
If we already find the offset, normally I guess we should control like the instruction pointer. So this would
mm-hmm.
be AP. Um, but I was just having like troubleshooting some exploit pipe issue things, so I didn't follow the last bit. But normally, if you already find the exact offset and you have the size of your buffer you want to overflow, normally next stop should be to try to control the EIP.
Yes, so yeah, sort of. So we have, let's say we have these three options. Which one should we pick? So the first option should be get the instruction pointer in control and do a buffer overflow vanilla type. Second, get a cyclet pattern into memory so we can get the memory offset values, and in return get the offset for the structure exception handler. Or three, create a shellcode. What should we do next after we have this crash? Option one, two, or three?
Two.
Two. Okay. Anyone else? See one more two. All right. Anyone else wants to give it a go? Okay, then we go for option two because that's the correct one. So if we take control of the first option, if we take control of the instruction pointer, then of course we will choose do a vanilla buffer overflow, right? And then we will skip the whole structure exception handler method. So if we take control of the instruction pointer, then we will find the problem that if there is an exception handler, the exception handler will be raised, and then when we try to jump into the stack, we are not going to be able to if there is an exception handler, and we have also overridden the exception handler. If we choose create a shellcode, there is nothing there is nothing there because we choose have a shellcode, but we don't have it where to put it or a way to execute that. So that's correct. Um, so now we have the cyclic pattern. We know how to create a cyclic pattern. So let's create one just for the sake of it. So we're gonna create a pattern of 6,000, 6,000 A's or something like that. Then we go to the log. Now it's gonna take some time. And then it's gonna create the pattern. How many A's did we send? Here? isn't 9,000. Oh, that's a lot of A's. So this is the cyclic pattern. So if we copy this cyclic pattern and then we dump it into the browser instead of A's, like I just did a second ago, what's going to happen is that when we execute it with our parent, if we when execute this with our parent, um, we will get something like this. And then we will know where is the structure exception handler memory offset. And by having the structure handler memory offset, then we can override that memory offset, yeah, with our uh, with our champs right after that. So that's about it. That's the trick. And then the short jump is always the same. And the next step after having those offsets will be to get the pop-up reds. So remember, to get the pop-up reds, we need to also use ERC. By the way, guys, you can find the pop-up reds manually, but it's gonna take you a while because you have to look for pop-up red values in memory. That's why we are using scripts. But if you just disassembly this and you see the opcodes of this one, let me show you. For example, one here. I just run the pop-up red, and let me see here. If you go there, yeah, I just click one and you see pop-up red there. But that's part of system32 DNS API.dll. So all of this contains pop-up red, and these DLLs are loaded into memory for this program and within this program. So if I click on this one, on this memory address, I will see pop red. There, click pop red, right? Alrighty. Closing it. And the next step after I have that, after I have my pop red, I will just add it into my exploit. With the buffer size and the knobs, I need to make this math, and then you don't have to. I mean, it's not required. You are not required to add this, but if you use hard-coded values, then you cannot replace the shellcode on the fly, right? If I just add exactly the number of knobs that I want and I take the length of the shellcode or not, I can choose execute it, but I cannot replace it on the fly. That's why this is the value that is changing, the value of the knobs. This is changing. This is changing as long as the shellcode length changes. All right, then I'm just sending this through here, through the socket. So let's do something. Let's create a shellcode. Let's remove these two, and let's create a shellcode with exploit pack. So close, 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 and the program is not running. Try it. There you go. Run. And just for the sake of it, so you can see it on the debugger, let's attach it to a debugger, continue the execution, and now the program is running attached to a debugger. And now we're gonna go to exploit pack, shellcode generator, and we're gonna create a shellcode here. Shellcode generator, and then click here. We're gonna try these three, but first we're gonna try exec, then reverse, and then bind. But in no particular order, but in any case. So exec, then as soon as I click exec, it will allow me to type a command. That's the command that is gonna run my shellcode, right? The exit function that I want, exit process, that's correct, or none. And if you don't use exit function, you might just hang the program. And then if the program is hanged, if the program closes, then your execution is done. So if I choose get execution, I'm gonna type a command here, like always, calculator, but you can run whatever you want there. And then as a bat char, I'm using the common bat chars as well. Remember 00, 09, 0A, because this is also a string. And choose to be sure, completely sure, and choose keeping the other bat chars for other type of exploit, format type of exploits. But it doesn't matter if I only have like this one or this four, then it should be enough. But we can choose leave it there. It doesn't matter. And then click on generate. And then we get the shellcode generated with this command. It's also giving us the size. So I'm going to copy that, put it here. And then remember, in order for the exploit to get this one, in this shellcode, it needs to be called execute code. All right, we're gonna save it or press, we can save it or press Control S. And then of course we need the target. That's not the right one. I'm gonna copy that, use that as a target, and then click on execute exploit. Now I get a new exploit deployed. Here on the exploit pack console, I can see the output of the exploit. On their application log, I can see the interpreter, and under debug, I can see the exploit debugger. And now if I go to here, in the debugger itself, I can see that something happened because the program has been triggered with an exception. So here I can see that it's reaching the SSL E832 module that contains my pop-up red, and here I can see my short sham, right? So if I continue now the execution, I got the calculator popped up. Okay, so now let's do it again. But this time, let's change the shell code and use, let's use a different shell code. Let's get a remote shell. All right. So now let's go back to it. And as far as I remember, yes, we only have the execute code shellcode. So let's add a new shellcode. And by the way, guys, the shellcode generator is still in development. So if you've seen something that you are missing or something that you want, this is going to be pushed into main, I think next week or something. Okay, next, yes, let's do reverse, and then we do bind. For reverse, I will need an IP address where I'm going to connect back and the port where I'm going to connect back, right? So exploit pack is listening to any or or one in particular, but any is fine, but I'm going to pick this one, 44.228.249.1. Say 44.228.249.1. Let's check it. 44.228.249.1. Yes. And should be like that. And then let's pick a port. Let's use the default one for exploit pack, but it could be any port, of course. reverse, and let's generate that shellcode. And then it says, okay, while generating this shellcode, it did found some bad chars, so it replaced it. So that was quite useful. So now we have this shellcode that is gonna try to do a remote shell back to this IP and this port. So like that, and then we do remote shell, and then we need the target. And let's check it. Yes, that's correct. That's the target. And then of course we need to spawn a listener for that. There you go. And well, it's gonna be on this port. It's the default one, but as I said, it could be any port. Now we have a reverse shell listener here, and let's run the exploit. Says new exploit deployed, and as soon as we get a shell connected, it says happy hacking, and then I'm connected with the remote shell to exploit pack on that to that machine through the exploit. All right. And then let's do one more, but this one is going to be a bind type of shell. So instead of because now what happened is that I was connecting this program. I execute my shell code, and the shell code was connecting back to a socket to exploit pack. Now let's close it to make it more clear. Now we're gonna open a port and connect to that port. And as soon as we connect to that port, it's gonna drop us, it's gonna pipe to us a shell. So, well, we need to make the shell. I'm gonna replace this one. I can also remove that one. So let's go to shellcode generator, do bind, and because it's bind, I will only get the port. I don't know, 9999, generate, copy the shell, I pasted it on the incorrect place, right there, and then remote shell, it's gonna be remote as well, but this one is gonna be a bind type of shell. And we're gonna connect to the port 9999, so the shell code port is gonna be 99999. And then of course we need the target IP where the port is running. There you go. And now execute. And now we have the shell here. And as soon as we click on it, we get remote shell. And as we open it, we open a socket against that port, and we get the shell back from it. And there you go. That's how you make a structure exception handler exploit, and then how do you implement that into exploit pack. If you made an exploit and you want to save it on exploit pack, you always have the chance to backup exploits, and then you can import new modules and then load it back. So it will create a zip file for you of the exploit plus the XML file. And remember, to use the language that you wanted, so it doesn't have to be Python. So when you create your exploit inside exploit pack is intelligent enough to not force you to learn Python. So you can use either Python, Ruby, Go, any language. But remember to put it here on top. So exploit pack will know which interpreter plus the path where that interpreter lives. So you only have to follow this structure, but let's say you do it in Go, just create this simple structure, the arguments, and then put here the interpreter that you want to use, Ruby, Perl, PHP, it doesn't matter, it could also be Bash, it doesn't matter. So whatever language you prefer to write your exploits, you can use it within Exploit Pack. Um, okay, so I think that's about it, guys. Do you have any questions for me? No questions? Any feedback then? Have you enjoyed the training?
Definitely. Yes, of course.
Also, awesome. Thanks, Enzo. And anyone else? Oh, thanks, Vinay, and thanks, Austin. Okay, awesome, guys. So, what's next for you? So, I'm sure that you might, it's quite still early for some of you, so you might have feel like it was a lot this today. If you didn't have any SH type of knowledge for exploit development, that it might be a lot for you to digest. But remember, I'm going to share this so you can also try it on your side at your own pace. And as you can see here, these are created in such a way that you can first go step one, do the crash, step two, add the pattern, step three, add the pop-up red, step four, add the shellcode, and at the end of it, you should get execution, either local or remote. And after you have done all of that, then you can add your exploit to exploit pack. You have the ERC commands here that you can use, change the author and the folder, but these commands they do apply to you, so you can follow. And once you have all this knowledge, then you can apply all of this to other exploits. And what I would recommend you guys is that you, after you have successfully done on your side these two exploits, to try out a different exploit, same SEH exploit, so you can try it with a different program. So it's not only R or Echat server, but you can try it with a different program, right? And these concepts apply for everything else, right? In terms of exploit development. And yeah, I think that's it. And of course, I would recommend you uh, before going into any of this, always do a warm up, open the debugger, try to see some assembly, do a crack me, an easy crack me, or start ramping up the level of your crack me's. You start playing. All right, guys. It was awesome to have you on the training and wish you yeah, successful yeah, next adventures. Okay, guys. Thanks.
Thank you, Juan.